Good afternoon, everyone. Thank you very much for being here today in another seminar of the Astronomy Department cycle of seminars. Today, we are very honored to have the presence of Bruno Diaz here today for presenting his work. Many thanks, Bruno, for being here. And I will really briefly introduce Bruno. He's a professor at Universidad Andrés Bello and Cata in Chile. He leads the VISCACHA survey and chairs the SDSS VLVM working group. He was also the president of the Chilean Astronomical Society. His research focuses on stellar population, star clusters, and the Magellanic Clouds. So whenever you're ready, Bruno, you can start.
Thank you very much, Maria, for the invitation, for the introduction. Thank you very much for you to be here today. This week, we are in the VISCACHA survey and mosaic perspectives workshop. So that's why we are here. So we heard from us going around, a lot of people going around this week. And also we are offering this public talk. So all the Astro Meio-Dia, Astronomia para Todos, Seminário, it's all flooded with VISCACHA and mosaic people going around. So tomorrow I have Thiago, tonight we have Lucimara also talking. But today I'll be focusing on the VISCACHA survey. And for me, personally, it's a pleasure to be here. I spent 10 years of my life in this room here in office. I working with Beatriz Barbui here with my undergraduate, master, and PhD. So I have many histories, many stories, many memories. So it's good to see all the professors and the colleagues here that became professors now also. So I'm very happy to be here. So I hope you enjoy this as much as I do. This is the meeting that we are here. So just thanking also Fapesp and Beatriz and all the colleagues here to help us being here to discuss. So before I go into details, I invite you to stare at this image, because sometimes you are just kind of in a rush, going to many tables and catalogs and codes and so on, but you need to take a breath. And so why do we care about the Magellanic Clouds? So why do we study these galaxies, those stars? So I think that it's important for us to understand that. And something that I'll repeat here that's something I told in the meeting, is that sometimes we wonder about the galaxies there, that, okay, we do not understand why they are merging, why they are evolving, why these stars form, but do you think that the galaxies care? They don't. They will just keep evolving. They will just keep, even if we do not understand why they are merging, why they are behaving like that. So my point here is astronomy and science is not about only the galaxies, the stars, the dark matter. It's about us. It's about us human beings trying to understand the universe, trying to understand all of that. So science is knowledge, in other words. So we are trying to acknowledge, to understand, or to try to find ways to explain the universe and something like that. But if we cannot explain, it doesn't mean that the universe does not exist or does not keep evolving. So it's about people, right? So I think that collaborative astronomy is something that's very important, that we get along with people. And then, of course, we have to study physics, mathematics, and going to be open-minded for the open questions and to try to find the correct big questions that we want to pursue the answers and build instruments and collaborations and so on. Of course, this is part of the answers, right? But I think that the most important thing to keep in mind is that we are people trying to understand the universe and sharing this knowledge, right? So me in particular, so I am involved in many parts here, collaboration mostly. I'm leading VISCACHA and the LVM, but I'm also touching and collaborating in other groups using different facilities and so on. But I'm not the only passionate about the clouds. And I bring this timeline here just to show this. These are my personal compilation. Maybe it's not complete, but it's interesting to see the frequency of the meetings, the international open meetings dedicated to the Magellanic Clouds, right? So from the 60s up to today, the past you can see here, kind of 20 years between the first and the second, and then a couple of years and so on. And nowadays, don't know, even 2 meetings per year is happening about the Magellanic Cloud. So a lot of people are caring about that. And this is my explanation that we had the big telescopes coming to Chile in the 60s, right? In Australia, there was the radio antennas there detecting the Magellanic Stream and also the Magellanic, the leading arm. So that's kind of these gaugeo structures that are gigantic, 200 degrees in the sky. And then there was there was the explanation, some dynamical models trying to explain why the Magellanic Clouds are in the neighborhood of the Milky Way. So there was a revolution here at that period. And then we had facilities, telescopes that were large enough for meter-sized telescopes, 2-meter-sized telescopes that were dedicated to photometric survey. So there is a huge amount of data, a change of paradigm in the way we do science in astronomy, and this led to many surveys, right? So we had too many surveys, and especially here when maybe the 8-meter-sized telescopes were becoming more and more important, and the 4-meter telescopes started to be more dedicated to surveys instead of dedicated particular targets. And then you have a boost of many surveys with different wavelength range and the coverage and photometric depth and so on. And now we have more. We go to, I don't know, Euclid, hopefully Roman as well, some other spectroscopic surveys already going on, astrometry with Gaia, and VISCACHA is fulfilling here also this, a gap in particular here. About VISCACHA itself, so the project that we are talking about started here with 4 people that you may know, myself included, and also Francisco Maia, who is in Rio today, João Francisco, who is in Minas, and Leandro in Bahia. So Leandro and I were looking to the SMC, and João and Francisco to the LMC, and then we looked at each other. Well, you're doing similar science cases, we know each other, so let's do it properly. Let's make a survey out of this, and that's what we did. And all started because we have SOAR here with a huge portion of time for Brazil, and then at that period, 2013, there was the science verification of an instrument that's called SAMI, which contains a laser for adaptive optics, at least correcting the ground layer atmospheric turbulence. So it enabled, the perfect science case was the Magellanic Cloud star clusters, because of the field of view was perfect for the size of the clusters, and this correction with the image quality was great to resolve, spatially resolve the stars in the cores of those star clusters. Because all those surveys that I showed before, they were limited by the atmospheric turbulence, so they cannot resolve those stars in the cores. And then we are doing the survey to pinpoint targeting each cluster there and to resolve and do deep photometry, right? So the team is growing. We are doing meetings, different places here to also boost collaborations, invite students if you want to have many projects and so on, colleagues. So we have plenty of data and knowledge. So this is the picture of this week. So we had the Mosaic people and VISCACHA people together thinking about the future and what we want to go from here. Some numbers here, because I started this seminar talking about people, so I will just invert a bit. Instead of going to the science questions that I'll go a bit later, I'll talk a bit about the people and the numbers and the project itself, and then if you give me a minute, I'll go to the main science cases there. That will be more exciting. But a few numbers. We have just finished the main observations of VISCACHA, so congratulations to the team, because that was a big achievement. 12 years of observations is not anything. It's like big achievement. That was accumulated more or less 700 hours of telescope. I believe it's the group that heavily used SOAR there. People were happy that we're done, I think. We had more than 300 clusters observed, 300 gigabytes of files with 16,000 images there to process. And we have currently about 50 members in 10 countries. And just a quick note about this efficiency here. This efficiency is about the amount of nights that were allocated. Out of this, about 70–80% were possible to observe with SAMI. Why? Because SOAR doesn't have a service mode, it's only classical mode. So imagine the AO, we have specific conditions, so you have classical mode, visitor mode. If the night is not good, then you have to go for a backup program. So there is this, and there is also the quality of the photometry. If the turbulence is so high that we cannot achieve a very good precision, then we rather just use the public catalogs from the other surveys that will be the same, because it's limited by atmospheric turbulence. But the image quality that is very good, that means that VISCACHA has the images in the photometry better than anything else available in the world. That is about 80% as well, 70%. So when you multiply these things, we come up with this efficiency number here. That's rough number. But this, talking to other surveys, this is very good. This, of course, I will not read that, but we have been publishing a lot. The publications are growing. I mean, the number of papers per year is growing. Not only papers, we are also producing catalogs of cluster parameters and photometric catalogs. So far, it's a small portion, but we are working on have a public release of the survey products, and we are also producing software and more to be released. In terms of students, we had one master thesis defended and a couple of PhD theses defended. Some of them fully dedicated to VISCACHA, others dedicated one chapter, one paper or something. But we are working on human development as well. And one strategy that we use here on teamwork, let's say, to coordinate big efforts. Just one example that was recently, super recent, that was a target to be ready for this week. So people are very happy. So I just want to share and thank the whole effort here. Is about the data reduction of this 12 years worth of data of the instrument in SOAR. This was done in the past 9 weeks. So of course we had read papers, we have data that was reduced and fully processed and so on. But now we were working, as I said, on a homogeneous data analysis and to prepare for the future public data release. So we wanted to have the same version of the pipeline and everything. So that was only possible because you could coordinate the team. This is one of the products that we are releasing as well, which is the data reduction pipeline for SAMI. The idea is that this will be released and installed locally in the SOAR computer, so people who are observing with SAMI, they can just reduce the data right away and have some quick analysis that are done during the night to make some decisions maybe, and so on. All of the information, I invite you to visit the VISCACHA website if you want to know more, and also our contact mail. Right, but this is about people, man. I'm sure that you want to know about the science. So what all these people are doing, right? So why do we care about the Magellanic Clouds and why the Magellanic Clouds are relevant for anything at all? So big picture, in the 70s, there was this antenna there in Australia. People were doing this H1 all sky map, and they realized that the sky had some patches and some trails of gas, and later they built a larger antenna, could have higher resolution, better analysis tools. But here I just overlap the two maps from the 70s and the 90s, showing same thing with more details here in pink. This trail part here is left behind the orbit of the Large Magellanic Cloud here and the Small Magellanic Cloud here. So we have these two galaxies that are the most massive satellites of the Milky Way, and they seem to be orbiting the Milky Way in this direction. And with this leading part of the orbit, with this trail of gas that was really hard to disentangle because it's crossing the Milky Way disk in the line of sight. So imagine analyzing that, say, oh, this gas is from the Milky Way, this is from the leading arm. Was really hard, but this was really, really clear. They are 200 degrees wide, or 200 degrees long. And this is left behind the orbit, and this is guiding the orbit, let's say. So there is room pressure stripping. That was, at the beginning, people thought that it was only room pressure because they confirmed the Magellanic stream, that's called this thing here. But when they confirmed it, they said, okay, so if you have opposite directions structure, that should be kind of some tidal stripping taking place as well. And if you're talking about tidal stripping, you're talking about gravity. If it's changing, it's moving the gas, it should be also moving stars, right? So if you have mass, you should be moving. So there were many, many groups there looking for the stellar counterparts of these structures or how the stars were affected and in this big scenario, right? So long story short, what I have today is this scenario where the LMC and the SMC are a pair of galaxies that were far away from the Milky Way, and they are now infalling to the Milky Way potential, right? So it's kind of a pair of galaxies, they're infalling to this. One of the, for my understanding, I think that the compelling evidence for that was this, that a group predicted and observed what they call the LMC wake in the northern sky over density. Essentially, the LMC has 10% of the Milky Way mass, so the gravity there disturbs the halo, the stellar and the dark matter halo of the Milky Way. So they could observe that concentration because of dynamical friction and so on, so you can concentrate a bit of this stars and also the dark matter. They predicted, they observed, so this could only be possible if the LMC is passing once there. Because if it was orbiting many times, maybe these effects are diluted. But they could observe that was pretty nice. And then, with this idea in mind, cosmological simulations and hierarchical mass assembly of the Milky Way predicts that that should be working in different scales. So you should have this big mass of Milky Way with the LMC going down and also other smaller galaxies. And that was only possible to confirm with photometric surveys detecting those galaxies, the existence of these ultra-faint dwarf galaxies, and with Gaia proper motions to have the dynamics, right? So if you have this kinematics studies plus their positions, what we have today is a map like this that shows the dwarf galaxies kind of in a preferable orbit or positions here around the Magellanic Clouds, right? So that tells us something that it's very interesting. And some studies have confirmed at least a couple of ultra-faint dwarf galaxies that are consistent with being satellites of the LMC. So in other words, the LMC is falling to the Milky Way and bringing the SMC and a couple of smaller galaxies together. So they have a system of small galaxies that are falling to the Milky Way. So that's the kind of the big scenario. There are, of course, some models trying to reproduce that. In the big picture here, all these big models, they're able to reproduce roughly kind of this large structure, right? So you see the observations on the top and the simulations on the bottom about the gas structure, right? So this, we had in the past some competing paradigms and scenarios. I would say that both of them could reproduce this big structure. So that part was easy. The hard part is the small scale. So this is where the observations are crucial because we require create a 3D structure in kinematics to provide some constraints for the models, and they will have a hard time to explain it, right? But we need to provide those models. And just a note here, because you all always talk about women science and so on, and especially for the students here to pay attention that this woman here, Cortina Besla, she did her PhD thesis to define this first infall scenario that didn't exist before. So she's responsible for this idea that became now the current paradigm of this formation. So that was a revolution in the field done by a PhD student. So just for you to feel encouraged to do your great PhD thesis there. Good, but this is the big picture, cosmological scenario, extragalactic in redshift 0, if you may. Sorry about that, but I usually call that. So we're talking about galaxy interactions in our neighborhood that we can study pretty much detail, and that could have consequences in our understanding in higher redshift, where we don't have the resolution, although we have statistics, right? But the star clusters that we study in VISCACHA, we can understand them as a population, and then we can study this type of things and constrain a bit of the 3D structure of the galaxies, their kinematics, and then think about the galaxies themselves. But also, if we study the star clusters individually, we can study stellar astrophysics, understand how the clusters themselves evolve and what is different to learn in the Magellanic Clouds that we cannot find in the Milky Way, for example. So here, in the Milky Way, what we learn from the books is a dichotomy, right? So we have globular clusters that are massive, old, round, and so on, and they are the halo and the bulge, okay? And then we have the open clusters that are currently forming the disk of the Milky Way in the arm, so they're young, they're lower mass, they're not super round. Okay, but if you go to the Magellanic Clouds, what we find there is, for example, a very old globular cluster that's not globular. So it's an old cluster, massive, but it's a bit elongated. It's not globular. We also find a massive cluster that is a bit round, but it's not super old, it's younger. So my point here is that this idea of the definitions of clusters in the Milky Way, it works pretty well for the Milky Way, but you cannot extrapolate that for all galaxies. So I just call them star clusters, and then they have their properties. Then if you go here, not going too much in detail, but just to show kind of concentration parameter here for globulars and open clusters in the Milky Way, you see that you have some differences here. And this is the distribution of the same parameters in the LMC and SMC. So they kind of complement the Milky Way population. In terms of stellar mass of the cluster, you see the Milky Way globular clusters that are more massive, and on the top, the open clusters are less massive. And the massive LMC clusters, they are more or less in between. So if you're thinking about cluster evolution, maybe you need to complete the parameter space. That's the place you go, because there you can resolve stars, can observe them, photometry, spectroscopy, astrometry, can have pretty much details of that. This you can appreciate a nice image in the background from VISCACHA, even with background galaxies, resolving stars in the core of the cluster, and so on. Just a brief summary here. You can do many things. Kind of this is radial density profile, surface brightness profile, so structural parameters of the clusters, the color magnitude diagram, so you can do ages, metallicities, distances, even extinction, and also here luminosity function, mass function. You can derive mass laws and so on, and you can derive many parameters from star clusters. And if you use them as a population, you can trace the 3D position of them and so on. So, okay, but star clusters are interesting. They're powerful tools. We can observe them in the Magellanic Clouds. And then why do we need a new survey? Right? So why do we need a dedicated survey? So I listed there many surveys, many photometric surveys. So why do we need another one? So here's the limiting magnitude versus the image quality, right? So in arcsecond here, how much you can reach in the PSF, full width half maximum. So with the 2-meter size telescopes, you can reach not the oldest stellar populations at that distance of the Magellanic Clouds. With the 4-meter size telescopes, you can reach the oldest stellar populations. But they're all limited by the atmospheric turbulence. Okay, could go to space. Gaia, yeah, but Gaia is not very deep and doesn't reach the old stellar populations. Could go to Hubble, right? So indeed, we have there are 100 clusters observed with Hubble in the crowded regions of the central parts, and also in very dense and massive clusters. Okay, but it's only 100 clusters. There is now Euclid and Roman that eventually could observe the Magellanic Clouds as well. But these are far away in the future or very expensive and very competitive to get, so we do not have enough statistics. And VISCACHA is fulfilling this gap here. So what we are doing is a compromise. So we are here from the ground with ground layer adaptive optic corrections. So you can reach about 0.4, even 0.3 if you're lucky in the night, arcsecond of image quality, which is enough for us to resolve the stars in the cores of the star clusters. Okay, so this is the niche that we're covering. All those surveys here, they are area surveys, so they're covering blindly a region of the sky. We are not doing that. So we are pinpointing individual clusters to complement, because the science that can do with them, the other surveys on the field stars, they're already doing that, and think a niche and exploring this niche. And we are still the only group doing that, so that I think that the VISCACHA data with this, well, heavily partly Brazilian telescope, I think that we are delivering very competitive science cases here. Just a quick note on the name, VISCACHA, right? So when we define the survey, we have to name it, right? So you may think, oh, it's cheating, right? Well, but acronyms nowadays is hard to have with the initials. What we wanted to do here was to put Brazil and Chile there in the acronym, because the telescope was there, the group was starting Brazil, and then we got this also idea that, well, Fernão de Magalhães was not the first to spot the Magellanic Clouds, right? So the name is just popular nowadays, but the words that himself, he didn't see the Magellanic Cloud, was Antonio Pigafetta, who was the one who was actually writing things there, and then we didn't think it was fair to name after him everything. And then we wanted to call the attention for that, and then there was other names for the clouds. So we got this Tupi Guarani culture here in Brazil that was before himself. And then we had Tapi-Uguá, which is the large cloud, and Coxi-Uguá, which is the small cloud. Good. So here I'm going to show the comparisons, and in practice, so you do not have to trust me. You can look at the images and the plots. Here is a cluster that's a bit sparse. So what difference does it make to have AO or no AO? No difference. So you see here that the VISCACHA CMD, the photometry is very good. The filters are not exactly the same, but, well, you can imagine it's very similar. But here's the dispersion, the photometric errors, and the photometric depth, the resolution. Everything is very similar if you have AO with VISCACHA and SOAR with 4 meters, and SMASH, which is using Blanco, the DECAM, with 4-meter telescope as well, very close there in La Serena in Chile, same region, same skies, with a very good night. They can observe this, and they will deliver, if you do the isochron fitting the same way, and the membership of the stars here, the parameters are very similar. Okay, so we're not gaining a lot if you're repeating observations that could be done for sparse clusters. If you go to a bit more crowded cluster, this is the observation from VISCACHA. I show here the difference between AO turned on and turned off. So you can visually see the central part here. It does make a difference. You can go deeper because then you can observe the fainter stars and so on. Here I compare the CMDs in the outskirts. So I put these rings here, and then the left CMDs are the ones from the stars in the outskirts, and the right CMDs here are the ones in this inner circle. So you can see that in the outer part, they are equivalent, right? But as you go inner and inner to inner parts here, you start losing the faint stars, and eventually you cannot observe the stars if you're limited by the atmospheric turbulence. So here's where VISCACHA makes a difference, okay? And then if you're really, really crowded, you better go to space. Okay, so it's ground layer atmospheric turbulence is not a miracle, okay? So you can have more statistics. So today what we have in the literature is about 100 clusters observed with Hubble and 300 clusters observed with SAMI. And because of this time limitation, it's not super efficient to have 300 clusters in a year, right? So it took 12 years to get this. So we had to be smart also in the coverage. So Hubble was concentrated mostly in the inner parts, where Hubble makes a difference. And we decided to go to the outskirts of the clouds, also thinking about these effects on the galactic structure and the tidal stripping and so on that are more marked in these outer regions here. So we are thinking about the individual clusters and also the populations in the galaxy themselves. So now I'm going to present a couple of discoveries that we have done already using VISCACHA data. So just chose a few cases. I'll try to explain different science cases here. So one big thing that we got that actually started with my PhD thesis with some hints and then I had my own PhD student to finish the work with more data and accurate. So it took a lot of time to go from the initial thoughts to the homogeneous sample with high quality and so on with SUMI. But there was a big discovery that only using, like, pay attention to that, measuring ages and metallicities of star clusters, CMD, isochron fitting, simple as that. From there, we got an evidence for a major merger 6 billion years ago in the SMC. That was a big thing that for us was like, okay, so now we have the evidence. Now the next step will be modeling it. It's harder. But the evidence, let's see if you're convinced as we were. The ages and metallicities of star clusters in the Small Magellanic Clouds look like that. Okay, so this is homogeneous. So this is not errors of the measurements. The errors are there, but the spread in metallicity is real. Okay, and all these lines are chemical evolution models that are trying to explain the SMC. And you see that they fail miserably because there is no single line that can explain everything in this dispersion. But you can appreciate that the different lines here, they kind of, together, they kind of explain this spread. So there are many people trying to explain that. And then they could not. So during my PhD, what I did was to come up with a framework to study this region by region. Because I realized that azimuthally, if you go around, this is the distribution of star clusters in the SMC from the BICA catalog. So all points here are clusters. Okay? So this is the central bar of the SMC, the main body. And then you can see that azimuthally, we have kind of voids here, and then a group of clusters, and then have a stripe, and so on. So this green part is the Magellanic Bridge that connects to the LMC that's far there. Then have an opposite region here, and then have another region here. So let's see what we have. And then curiously, if you have here the age metallicity relation of all clusters together, they have this spread, as we saw before. But if I isolate only one region, and I started with this that I called West Halo, then the dispersion is much lower in metallicity. Okay? And all of this using seeing limited photometry with SOI. Okay? And with a low number statistic and so on. So, okay, so this is something. Let's go for VISCACHA survey, get more accurate and more statistics and so on. And then, long story short, that was the result. So the West Halo and also the Southern Bridge, they share a similar low dispersion, well-traced age metallicity relation from 10 billion years ago up to today. So usually we would expect that as the time goes by, the stellar populations reach each other, and then you have the metallicity increasing. But there was a big metallicity dip here of 0.5 dex metallicity. And we tried to get chemical evolution models to explain that, and that was only possible if we had an infall of 10 to the 8 solar masses gas with pristine metallicity. So that was huge. So then it mixed up and formed the recipe. And this type of mass is what we interpret as a major merger in terms of a 1:4 mass ratio. And then what we are working on, and then we need models to do that, is that apparently what we know as the SMC today is the result of a merger of two galaxies. And if you come back to the introduction and you think about the LMC with lots of small galaxies together as a group in falling to the Milky Way, it's not super crazy idea to think that these small relative velocities there, something crazy is going to happen. Okay, and then, well, I'll just skip that. But if you look to other regions of this framework there, for example, the Wingen Bridge. This is the part that is connecting to the LMC and has lots of gas here around. If you look at this region, how does the age metallicity relation looks like? That's the contrast. So the blue line is the one that I just showed you in the West Halo and the Southern Bridge. If you go to this region, this is the red line, completely different. So now you can see that this intrinsic metallicity dispersion can be explained if you isolate these different regions in the outskirts of the SMC, analyze them region by region. So each region there, for some reason, they kept this history there imprinted. That's the hard part to explain. That opens more questions, right? But different regions here show different chemical enrichment histories, and with metallicity dips that coincides with the formation of the Magellanic Bridge, Magellanic Stream, a major merger there in the southern part. So we are tracing the past history of the SMC. Okay, I think I will skip this to go to another part. But if you're curious about the high resolution abundances here, so just skip that. But there are some, if you want to know more, you can ask at the end. So, but we discovered a major merger 6 billion years ago. So that was a big thing. Another science case now. So this one is also related to these interactions between the two galaxies. There is a statistical fact, let's say, that the LMC stellar populations, the field stars, they cover different ages continuously. So apparently there was star formation, maybe with bursts and so on, but we have ages everywhere in the parameter space. That's not true for the star cluster population. So apparently the LMC formed some star clusters more than 10 billion years ago, and then stopped, and then 4 billion years ago started to create star clusters again. Nobody knows why. Okay, so there is this age gap that's called for the LMC star clusters between 4 and 10 billion years of age. And then people are wondering, okay, so what's going on there? And then from time to time, someone discovers, okay, there is one cluster here with 6 billion years, another with 9. Okay, so, but the confirmed clusters are 3 or 4. It's not much. So there are surveys now, for example, the STEP survey is trying to account for that, but they promise something that they're not delivering the paper yet, because I'm not sure if they will achieve that, because the STEP survey is done with the VST telescope, which is 2 meters in Paraná, and seeing limited. So they're seeing these are not great. So I'm not sure if they can reach deep ages, but they are arguing that this may be just a statistical limitation because you're not observing clusters enough. It's still to be seen. What we did in VISCACHA was that we have homogeneous, we have deep, we can measure those ages. And then we discovered one cluster that's called SL2, and is the first one that is towards the SMC. So this is the sky distribution of the LMC. So we have all these clusters here. Some of them are confirmed, some other are candidates, but these are the age gap clusters. And you can appreciate that they're all on the outskirts and towards the north. We discovered the first one that is towards the SMC, so connecting here with the bridge. And it's also far away from us. The LMC is 50 kiloparsecs away from us, and the SMC is 60 kiloparsecs away. And the SL2 is about 60 kiloparsecs as well. Something here. So what's the origin of those guys? And then if you look here, I'll not go into much detail, but just to point, if you go to ages and metallicities, and also the ages and masses, this cluster is more consistent with the SMC bridge clusters than it is with the LMC. So it looks like the scenario that we're working now is that apparently at least this one, then you can extrapolate for the others, the age gap clusters should be a population of clusters captured from the SMC, right? So we are going from theories that are loose, people are trying to understand what's going on, to a piece of evidence that can change the course of the next papers and studies there. So that's only possible because we have accurate CMDs and can derive ages and can trust on those parameters, and also masses and metallicities and so on. Another science case here that we also are contributing, more going towards now stellar activities and stellar evolution clusters, is about the main sequence turn-off. When you think about the CMDs, the color magnitude diagram, you know that we have the main sequence, and then as stars are evolving, then we have this mark the point of the turnoff. That is an age indicator, right? So what's going on here is that this turnoff, in this left case here, it's a young cluster, and there is some spread of color here in the turnoff. So we could think that this is different ages of the stars, but actually for young clusters, that could be something else. For example, B star, rotating stars there that can cause this. If you go to the very old globular clusters, if you see this, like in Omega Centauri, this is actually many generations of stars that were formed, so have different ages there. Okay, but this is not what we are discussing here. We are getting actually the intermediate age star clusters that show this phenomenon of a spread in the turnoff. Here is just a couple of examples from Hubble studies, so showing this spread there, but mostly for ages between 1 to 2 billion years. So there's a specific range of ages where they show this phenomenon, right? So what's going on there could be age spread, could be stellar rotation. So lots of studies are going to this direction. For example, in 2011, there was some big discussions there in the past few decades about this. And the reasoning here is as such. So you have the, let's say, the bright or the bluer main sequence turnoff and the redder. So the bluer could be the younger case, okay, if you think about ages. And then if we have two generations, usually the stars are formed in the central parts of the clusters where we have the potential depth there and more material of gas. So if you have the younger population of stars, they should be more centrally concentrated than the older population, right? So they are looking for the distribution, the radially distribution of those stars versus the other one, and they found that the bluer stars are more centrally concentrated than the redder stars. So their conclusion there was, okay, so age must be the most important phenomenon here. Rotation, they had a similar argument that you can read there or ask later. So apparently age seems to be the case. Another phenomenon or another parameter that we can test is the escape velocity and the mass or the total mass of the cluster. And what's the reasoning here? If you're thinking about ages, right, so different generations of star forming, it means that you must be able to keep the previous generation self-contained in your gravitational potential, in your cluster. So that means that when you have the first generation of stars forming, then have maybe supernova winds or something like, or even the two-body interactions between the stars. So if they're kicked off from the central parts and they're kind of kinematically getting hotter and hotter, their individual velocity should be smaller than the escape velocity of the total system, right? So the escape velocity here, as the larger is the higher is the escape velocity, the more likely the stars to retain those initial populations, and therefore you should have like a wider extended main sequence turnoff. And similarly for the mass, if you have larger mass, you should be able to keep those things. And then that's why we have some plots like that showing in the vertical axis, not going into detail on the numbers, but this is a measurement of how the width of this main sequence turnoff. So you can see here that the mass and the escape velocity, they scale with these points here. So each point is a star cluster. So apparently there is a relation about this. So if you think about ages and this retention of the stars, looks like age is something that could explain that. But there are other people, okay, so if that's true, you're scientists, let's prove that. And they were looking for clusters that are very young in the universe and see if you can form those different generations of stars, and they could not find that. They could not observe that. So if that's true, why that was true in the past and not true now? So the physics has changed? I don't think so. So they're trying to explain that in a different way. And apparently rotation is able to explain that, but maybe in the past we didn't have all the models. Now we have the stellar evolutionary models that contains also variations in rotation, but not only the speed, but also if you think about stellar rotation, you should have an equator plane that can be pointed at you, or the pole would be pointing at you. So depends on how is the orientation of this rotation axis. It also affects what we see in the colors of those stars, right? So there's some reasoning here. So it could be the colors, could be distinctions, or even some interior stellar activity. So if you have rotation, so even the outskirts of the inner part of the star with hydrogen, they could be feeding the hydrogen burning core, and that would kind of delay the stars to stay longer in the main sequence. Okay, so rotation is very important. So VISCACHA, what's doing here is to actually go down to the low mass regime. So usually these studies are done with Hubble, because you have high precision photometry, you can see these details and different stars and so on. And then people using this Hubble data, they are a bit kind of suspicious about ground-based data. So one thing is that we proved that we can do that from the ground. VISCACHA is performing very well with the photometry, so it's possible to see this phenomenon. And second, that Hubble usually go for the very massive clusters. But there is a regime here that you saw that maybe the low mass clusters, they show less of this width, but it should be possible, right? So what we are seeing here, and I think, yeah, so we have the two plots here. So what you're seeing here is that we have the phenomenon of ages, right? So younger ages, they do not show this phenomenon. For some reason, within 1 to 2 billion years, have this peak. So it's something happening with a specific regime of masses, right? So stellar, given regime of stellar masses, range of stellar masses, they are affected mostly by this rotation or this internal mixing, or for some reason we have this happening for this range of masses. And these different curves here, and then you see that the points or the clusters are spread out above these curves. This is the rotation velocity, so close to the critical velocity or is lower velocities here. So the age and the velocity are playing a role. And if you see here the masses and the escape velocities that we show this relation, you see that there are some outliers that do not show any width, right? So these are the yellow crosses. And why they do not show? Because they're too young. So the yellow crosses are here. Okay, so it looks like we have many characteristics playing a role, and VISCACHA is pushing the limits of the low mass regime, which are all these colorful circles here, are the results from VISCACHA. So you can appreciate that the trends are the same, and we are reaching here the bottom of the sequence where we do not find this phenomenon anymore. Okay, so we are contributing on this part. And I think this is the last quick point. The last science case here that I want to highlight is about cluster dissolution. So star clusters are a gravitational system of stars, as you know, but because you have different masses of stellar masses, they are interacting, and then sometimes, I don't know, have the dynamical friction, and then mostly the massive stars, they are sinking to the core, the low mass stars are leaving the star cluster because of two-body interactions and transfer of momentum, and then mostly those low mass stars, they are moving in general to the outskirts, and then you can think about what they call evaporation, because particle by particle, star by star, are leaving the star cluster. So these are internal phenomena. Can give more details, but this is kind of an internal phenomenon. But this could be boosted by external factors. So if you think about the Roche law of the Lagrangian points there of the zero velocity, that is dependent on the base potential of the galaxy. So if you have the star cluster and the SMC here, but then the SMC and the LMC are interacting to each other, it means that when you have a close interaction or close position, LMC plus SMC, then the base potential changes. So the cluster zero velocity potential and will change as well. So these external factors could affect as well. So what you're looking for is exactly those cases where the clusters were dissolved. And we are using this panel here of cluster mass versus ages, because we are expecting, and there are some models to support that when you have a low mass cluster, they will not survive for a long time. When you have a high mass cluster, it's less likely that it will be totally dissolved. And then in our first paper already, we discovered one case that is low mass and very old. Looks like that. And if you look at the mass function, here it's 1 solar mass, and this is going down, 0.8 solar masses. If you do a salpeter IMF, it should be like this pink curve here, so predicting a large number of low mass stars. And what we observe is that there's a very low number of low mass stars. Already corrected by all the completeness and all stuff, the observational part is checked. So it's a real detection that this cluster has lost a significant amount of low mass stars. Okay, so we spotted one cluster that is under dissolution right now. Okay? So in this regime for the LMC, it will be interesting because the age gap is right here where the VISCACHA can contribute a lot. So we are looking forward to see if maybe the age gap could be explained maybe by cluster dissolution. Who knows? There are many things there. And think about the future. So these were some of the results, right? So we are working on many projects, different scopes, as a survey does. But think about the future. So what comes next, right? So spectroscopic surveys, for example. I mentioned the LVM. LVM is an IFU that's covering, among other things, the Magellanic Clouds. And what you can do there is that a single spaxel of this IFU will give us a spectrum. And the spaxel of this, meaning a single fiber, has a size that's more or less the size of the core radius of a cluster. So in other terms, we are getting an integrated spectrum of this star cluster. And there are many groups, including ours, that have been done this in the past. Then we can compare this to SSP, so the simple stellar population here that we can predict ages, metallicities, and radial velocities all together from a single spectrum. So that's a precious data set also that will contribute to all the science cases that I mentioned before. Rubin is already in place, so that was 10 years ago. There was no Rubin, now we have Rubin. We can go very deep. We cannot resolve the inner parts of the stars clusters, but we can definitely go deeper than VISCACHA in the outskirts as the time goes by. So we are accumulating more and more data. So maybe if you find these clusters that are in dissolution, those low mass stars, they should have been gone to somewhere. Maybe there is a stellar halo around these clusters. Maybe there is even stellar streams, who knows? So there's lots of interesting questions to be answered there. And this is just the footprint. And also going to space, there is this new telescope that will be launched in 20 days from now. I think that it's already, the rocket should be there. Roman. So now that the cycle 1 proposal is done, I can tell that we applied for that. There was like 100 people team around the world. We didn't get the time, but we have a strong proposal and people are excited to keep applying for that. But there is also Euclid that will provide lots of deep and resolved photometry for that. And just to finalize here with some messages, as you know, we have the General Assembly of the IAU in 2030. So the next one next year will be Rome. So the other will be in Santiago, Chile. That is the 3rd time the history that's done in Latin America. So I think that's a big call for all of you. Think about ideas to organize a symposium there from Latin American people, groups, get together. I think that is a great opportunity for us to do science. And also the Magellanic Clouds are in the Southern Hemisphere, so I think that's the way we can do some contributions in this field. So thank you very much for your time, and I'm open for questions.
Thank you very much, Bruno, for this wonderful talk. Let's start with questions.
Thank you, Bruno, for your talk. Very interesting. I wonder whether the Magellanic Clouds have central clusters, like the Milky Way, and whether there is any evidence of supermassive black holes in these structures.
We are looking for that. Didn't find anything yet.
Neither the clusters nor the black hole.
It's the one thing, the first thing is actually, it's hard to find the center. That's the first step. We don't know where the center is. If you go for a dynamical center, you find one spot. You go to stellar density, you find another spot. You go for gas, you find another spot. So that's the first step. Even for the LMC, which is a disk with rotating disk. So let's see, with these larger surveys, we are looking for that. And maybe with the spectroscopic surveys, maybe you can have like a peak of velocity dispersion. That's the goal. That's it. But still nothing.
Thank you.
I have a question, maybe naive, but I don't know, about your first result you showed about the merger at 6 gigayear ago. How is that the stars are moving very slow that you can separate them, especially still after these 6 gigayears? How is that they are not already mixed and you can still take a piece of that and discover one population, took another piece and have another population of stars?
Great, you understood that very well. That's a very big question, and that's the natural and the big question that we need to solve now, because that was the first thing that came to our mind. I mean, okay, we see that, but how come 6 billion years ago and we still see the signature? So that's kind of, if true, that's a very strong evidence and hard to explain by the models. But one thing that's interesting that happened 6 billion years ago, the Magellanic Stream and the bridge were created afterwards, and we do not see the signature in the west halo and the southern bridge. But that happened afterwards. And then what happens? Well, it's here. Well, yeah. So the west halo and the southern bridge is here, right? That's opposite side of the LMC. The bridge is in this direction. So apparently this part was isolated when the bridge formed. And the Magellanic Stream is about, more or less here in the center, going north in this direction. So it's in the opposite side of the west halo as well. So this other big phenomenon that took place and distorted heavily the SMC, that took place after this presumably major merger, they happened in different regions of the SMC. So this is just kind of evidence, but it's up to the models to simulate and to see how likely or how that was possible. But definitely is a very interesting question to be. Yeah, we do have all the phase space vectors. So when all these conclusions that we had there, they are also consistent with what we call the tidal expansion of the SMC. So these external regions where the VISCACHA is observing show that, I don't have the slide super quick here, but essentially we show that this region here that's opposite to the LMC, they are farther beyond our line of sight and moving away from the LMC. And this region that's the bridge connecting with the LMC, it's closer to us, meaning closer to the LMC, and moving towards the LMC. So it looks like it's not rotation because there are different regions there. It's kind of really a tidal expansion. So it's also a piece of evidence for the models to explain. So something really big happened, and the SMC is really distorted. So we all knew that, and that's why traditionally people study the LMC, which is closer, brighter in a disk. It's easier. But the SMC, now that we have star clusters, we can do the 3D structure. And that's crucial because the SMC is 4 kiloparsecs wide across the sky and 20 kiloparsecs long in the line of sight. So the 3D shape is crucial in those studies.
Thanks for the talk, very nice. And I have a question regarding the dissolution of clusters, because, okay, this is a major issue in this evolution history, right, of systems like interacting systems like this, and environmental effects can be very important, right? Yeah. But what is the typical or expected time scale for the dissolution of isolated systems?
Mm-hmm. Yeah, so that's a very good question. If you have these OB associations, that should be a couple of million years. So these systems did not even, So you need kind of a critical mass to actually form that. But then it depends. That's interesting because there is not a single answer for that, because many cases depends on the initial conditions, because these two-body interactions, it's essentially you have maybe a binary, a hard binary, have a third star coming along, then you just transfer some kinetic energy for this third star, and the hard binary hardens, right? And then they sink to the core. If you have the same stellar black holes, if you have a large population of stellar black holes initially, because had like maybe the IMF was different, I don't know, have more massive stars, they have lots of stellar black holes around, so the interactions there will cause more evaporation of those stars as well. All of this depends on the initial conditions. So that's why you have the dynamical evolution of clusters. If you look to the globular clusters that are really nice to study that, and there are people using like blue stragglers, they are using that to measure the dynamical age of the clusters. We see that the chronological age of globular clusters are typically larger than 10 billion years, and still you have clusters that are really young dynamically and others that are really old dynamically. And old means that the mass aggregation, the concentration, the core collapse means that the stars are really, really tight. And they have all the same age. So the current conclusion that people have in the literature that it's heavily dependent on the initial conditions. So you see 10 billion years and there are 10 billion years and there are clusters that are still dynamically young. So this evaporation really depends on case by case, I would say, but could take billions of years.
Thanks.
More questions?
Yeah. Do you have any evidence of the difference in the IMF of the Magellanic Cloud with the Milky Way?
We are working on that, and there are some papers already published from other groups. One thing that we see is the present-day mass function first, right? So the IMF, the discussion, but apparently the salpeter for the high mass salpeter has a slope of 2.35, and apparently the open clusters and also the Magellanic Clouds cluster have a 2. So it's slightly different. And what we see, I don't know the explanation for that, but it's some piece of evidence that I've seen in the literature, and we're trying to study it deeper because we have different ages and so on. And one thing that we are pursuing now, also consistent with other papers, is to see the evolution of this slope. Like as we saw here, the cluster in dissolution, 6 billion years of age, I think, or 5, had this flat mass function because it was losing the low mass stars. So that's what we're looking for, this evolution of the slope. So if you're thinking about this paradigm of low mass stars go to the outskirts and they are lost to the environment, then we are looking for this slope flattening because of the low mass end. So we are seeing the evolution of that. But about the universality of the IMF, I think that's a big jump, and then we need to solve this first, to the present day mass function, and then go back to the stellar evolution.
More questions? If not, thanks, Bruno, again. Thank you very much. And we can continue the discussion during the coffee break. Thank you.
Thank you.